Okay, for our first session on managing risks and balancing trade-offs, I'm going to turn things over to Jen Humberstone from the Nature Conservancy. Jen, you have
Thanks.
until about 11 o'clock to navigate this exciting topic for us. So take it away.
Awesome. Thank you, Dan. And thanks everybody for being here, and for those of you that have been along for the last 2 weeks. We're really thankful for your participation. So as Dan said, the objective of this session is to explore the tools that help us put it all together, understand the overlap in marine life and fishing dynamics, consider and predict risk, and explore trade-offs. We've heard about observational data and how that data can be used to inform real-time monitoring needs, and how that data can also help us better understand population structures and trends in abundance and migration. In earlier sessions in this workshop, we have also learned how researchers are building from these observational data streams to develop models that can simulate the dynamics of whale distribution and fishery dynamics. And on Tuesday, we dug into social and economic considerations, where we heard about a range of impacts and considerations from the fleet. And we also heard from managers regarding the need for frameworks to evaluate social and economic impacts alongside conservation effectiveness. I thought this conversation on Tuesday was really engaging and provided a great starting point for today's session, which focuses on tools and methods for evaluating trade-offs of management approaches across numerous management objectives. The work you will see today combines much of the work you've seen in previous sessions, and the idea is to holistically evaluate risk and trade-offs and conservation and economic impacts across management approaches. These tools seek a science-based, rigorous approach to designing management to meet objectives for conservation and economic health of our fisheries. So, as in the past sessions, we'll kick things off with brief 10-minute presentations, and after that, we'll have Q&A as time allows, and then we'll invite additional panelists to our virtual stage here to join in a group discussion regarding opportunities and barriers to apply the science management frameworks, and what we can learn about data limitations and future priorities based on what we've learned. So to our presenters, a reminder that you'll hear timing cues. There will be a chime at 2 minutes and a bike bell when your time is up. And I will be pretty ruthless because I want to ensure that we have time for clarifying questions and a robust discussion. And our presenters today that you will be hearing from in order are Karen Forney from the NOAA Southwest Fisheries Science Center, Jamil Samori from the NOAA Northwest Fisheries Science Center, Chris Free from the University of California, Santa Barbara, and Burton Schenk from NOAA Northeast Fisheries Science Center. So without any further ado, I'll hand it over to Karen. Are you okay to kick us off, Karen?
I will do my best. Everybody hear me okay?
Yep, loud and clear.
Great. Okay. Well, that's beautiful. I'm going to move one little window around, but thank you. So I'm honored to be here. Thank you for this invitation. It's been really a great webinar series. And what I want to present today is some work that was actually led by Jessica Redfern, who used to work at Southwest Fisheries Science Center with us and is now with the New England Aquarium. So I'll be presenting this on behalf of our whole team. See if I can get this to advance. There we go. So humpback whale entanglement risk. That's the topic of this talk. And the motivation is that obviously with entanglements having increased recently, we really need to understand risk and the factors that can increase or decrease risk so that we can explore potential management measures and determine what's most effective. The analysis I'll be talking about today includes primarily 2 data sets. One was the humpback whale density model that I talked about last week in module 2. And the other is an effort of spatial fishing effort for the California Dungeness crab fishery that was analyzed and provided by Blake Feist and colleagues. The fishing estimates are derived from VMS data and landings. Our approach, which is regionally stratified according to the regions shown in the figure on the right, Washington and Oregon separate, and then several regions in California, is a commonly used metric of risk, which is that the risk of entanglement to whales is proportional to co-occurrence. So it's basically just a product of the estimated number of whales and the estimated fishing effort. So the humpback whale density model, just to remind, or for those of you who weren't on the webinar last week, this shows 3 different years, a period in late November, early December when the fishery would normally open. And the green colors reflect density, yellows are higher density, dark greens are lower density. And we can see that there's some variation from year to year with, in 2009, the whales had mostly left a large chunk of the coast. 2013, they were a little bit more persistent. And then in 2015, when we had actually increased entanglements, we did have more whales still present on the coast, and the model correctly captured that. We can also look at within season predictions for the model. And this is similar to a figure you'd seen before, but I've split it up by state just for simplicity. The top panel is Washington, the middle is Oregon, and then the southern has, the bottom one has 3 California regions. And this plot runs from November 2009 on the left to November 2013 on the right. And the black vertical bars show the start of the Dungeness crab fishing nominally in November. And what I wanted to show you is that this model does capture the seasonal movements of whales, so that in the wintertime it's low, and then in the summertime it increases, and then they move again. And there's some variation from year to year, but that pattern is relatively consistent across the 3 regions. If we combine all this into one very messy graph, with apologies, we can see that this pattern holds coast-wide, that there's basically concordance, and there's a summertime peak and a wintertime drop-off throughout all the regions through to 2013. But what happened during the marine heat wave when the entanglement spiked was that this seasonal concordance broke down rather dramatically, that whales were persisting along many areas of the coastline throughout the winter, and basically that U-shaped pattern disappeared. Jared Santora and colleagues published a paper on this just this year, and it described some of the oceanic and ecosystem factors that contributed to that. So what we wanted to understand is how this disruption affects our estimated entanglement risk when we put our layers together. So the second layer is fishing effort. These are landings-informed VMS data, and this is for California and Oregon only. We don't have access to the Washington data at this point. And I will walk you through this figure again. The time period is November 2009 through, in this case, late 2018 or mid-2018. And in this case, the y-axis is the VMS pings per square kilometer for vessels that are determined to have been Dungeness crab fishing. And I've numbered a few things here in this plot. I don't know if you can see my pointer. I'm trying to aid a little bit, if not, but I've numbered those just to make a few points. There are many things we can pick out of this, but I just wanted to make a few points. In number 1 there in 2011-12, we see sort of a typical peak of fishing effort in December through February. That goes for all regions except perhaps the South Central California region. And that's typical for most years in this time series, especially the early ones. Number 2, in 2016, we see that in purple, the Central California, the fishing peaked in April through May, so it was delayed. It was later because of the delay in the season start caused by domoic acid. In 2018, we also see a later peak. This is number 3 in Oregon and Northern California, and that peaked in February through April rather than earlier, as was it happening throughout most of the time series. So we're picking up patterns of variation in the fishing effort that occurred during these years. When we combine these 2 layers, the product of whales and the VMS pings per square kilometer, this gives us a relative measure of risk. So on the left, again, we're going from 2009 to 2018, and the y-axis now is a relative measure of risk. This is not telling us any probability that a whale is going to get entangled, but when the value is greater, there is a greater risk, and when the value is lower, there is a reduced risk. And again, I'll point out a few features. I've tried to color code this to aid you a little bit. From 2009 to 2013, so on the left side of the panel, we see that the peak risk occurred in Central California, that purple line, and that was generally in the November-December time periods. If we look at 2014 through 2018, Central California is still mostly the highest, but the overall risk has increased dramatically, almost doubled in that later time period. And it also increased rather dramatically for Northern California and Oregon in some years. Oregon is the blue line, Northern California, the green line. And again, to guide you, this vertical black line is November, just so that's sort of a fishing season. The other thing we can note is that in 2015-16, again, when the domoic acid delay was extreme into the springtime, we can see that in all regions, there was a delayed start to a peak in risk of entanglement during the fishery. So what does this do for us to look at this? This is hindcasting what happened in the past. Well, what we can also do is hindcast what would have happened to that risk if we had implemented a variety of management measures. And in the overall analysis, we looked at a whole suite of management measures. And today I just want to go through two very simple examples that have been discussed during our sessions. One is a delayed opening in the fall, which would act to reduce the fall entanglement risk for whales. And the other is an early closure, which would act to reduce spring entanglement risks. We can test any number of scenarios or combinations, but I just wanted to keep it simple since I only have 10 minutes. The starting point in this analysis that I'm going to show you is that during the periods when we delay or close early, the effort that would have occurred in those times we're just eliminating in our analysis. But we could also run scenarios where the effort gets redistributed or there are other types of shifts in this. So the framework that we've set up allows testing any number of situations. So jumping right into what a delayed opening would have done, and I've just arbitrarily picked January 1st because there was I could illustrate things best. We could similarly use December 15th or December 1st. The right-hand figure has 4 panels. Top left is for Oregon, and then Northern California, Central California, and South Central California. The bars indicate the risk with the management measure. So in this case, if we delay the opening to January 1st, and the black dots show what that risk would have been without any management measure. So what the risk was in our current estimated analysis with no effect. And a few take-home results. In Central California, which is this lower left panel, we can see that the risk reduction, so the difference between the black dots and the bars, is greatest in all years, which isn't surprising because Central California has an earlier start date. And so there is more fishing that would have been eliminated with this potential measure. In Oregon, there is a large risk reduction in 2014. Let's see if I can point to that here, this point here. And a smaller one in 2016, but otherwise very small risk reductions. And similar pattern in Northern California, reduction in 2016, but not elsewhere. If we look at the other end of the season, in April, so if we close the fishery on April 1st, in all regions that would have reduced risk. We can see that the bars are lower than the black dots. In 2015 in California, however, this would have virtually prevented any fishing because the fishery actually didn't really get going in earnest until April because of the domoic acid. But this gives us a sense of what magnitude of risk reduction we could expect with various measures, and we can pick April, May, whatever time periods we want for this. So the next steps in this are then to examine these risk reductions and relative to the cost of the fishery, because really what we want is to get measures that give us the greatest risk reduction with the lowest cost to the fishery. So in summary, the estimate of risk that we get by combining the whale model and the fishing data estimates do seem to identify periods of greater risk based on the entanglement records. Delayed opening and early closures could reduce risk. However, we do need to better understand and evaluate more fully how that effort might be redistributed into other months or not. And most importantly, the socioeconomic impacts of the fishery need to be evaluated relative to risk reduction. And Jamil and Chris will be talking about that more in their upcoming presentations next. Our analysis also showed that management solutions are likely to be region specific, and the optimal strategies may vary from year to year. But this tool that we've set up can help guide an evaluation of alternatives. And we're hoping that it will be helpful moving forward. So that's all I have, and thank you very much.
Excellent, thank you, Karen. I think because your and Jamil's work is so related, we'll move forward to Jamil's, and then at that point we can pause for questions. So also encourage folks to submit questions into the Q&A. Thank you. Hi, Jamil.
Thank you.
Take it away.
I noticed Jamil and I seem to be in the same place with our background, blurred backgrounds.
Ha. Can you hear me all right?
Yes.
Great. Well, thanks so much for the opportunity to present today. It's been a great couple of weeks. Before I get started, I'd just like to acknowledge the team effort across the Northwest and Southwest Fisheries Science Center, the West Coast Regional Office, University of Washington, and New England Aquarium that made this presentation possible. So thanks to all my co-authors. I'd also like to give those of you with short attention spans the take-home message right away, which is that the expected benefits to whales in terms of reduced entanglements, and the expected cost to the fishery of different management actions are not the same from year to year, and were quite different during a period of a marine heat wave from 2014 to 2018. The other take home is, yes, this is what COVID hair looks like. Okay, moving on. And before diving into the entanglement science, I just want to take a step back to give a bit of my perspective on what this module 5 is all about. And to me, this quote by E.O. Wilson, "We're drowning in information while starving for wisdom," encapsulates a lot of what I've been thinking about over the last couple of weeks, which is just being so impressed at how much data and information we have available to tackle the entanglement problem. But that without the synthesis and integration that we're seeing over this series of workshops, as well as what you'll see in today's module, that information can't be put to its best use for informing decisions. And I think you'll see what I mean a bit if we step away from entanglements for a moment and think instead about something that's on all the headlines right now, because it's hurricane season in the Caribbean. And there are many of these satellite images, like the one you see here of Hurricane Laura as it approached the coast of the US, as well as empirical measurements of wind speeds and precipitation that tell us what's happening right now. But without the synthesis and integration of this empirical data into models that provide forecasts of where the hurricane is going and how intense it will be, there isn't an opportunity for people and policymakers to make strategic choices about what to do about that hurricane, where what to do might involve sheltering in place if the hurricane is going to hit Louisiana and Texas and you're in Alabama, or it might involve deciding to evacuate at great economic cost, but hopefully to minimize risk to human lives. So these models aren't perfect either. They get the track right, but not necessarily the intensity of these hurricanes right. And I think that's the same of what you'll see in today's module, as well as what we've heard about over the last couple weeks. And so moving back to ocean management, one way that I use to think about organizing all of the scientific information that's available to inform decisions is via an integrated ecosystem assessment. And just to walk you through this process, it starts by asking, what do you want? And I heard this really clearly on each of the days of this workshop over the last couple of weeks. There are these twin goals of minimizing entanglements while maintaining vibrant fisheries. And in order to reach those goals, an IEA framework starts by asking, well, where are we right now? And we've heard a lot about that in terms of understanding the entanglement report data, ocean conditions, surveys that are being conducted, tagging studies, where fishing is happening based on the lived experience of fishery participants. And so it's with that information in mind that we begin to figure out, well, what are our threats towards achieving those goals of minimizing entanglements and maintaining thriving fisheries? And so that can involve things like what Karen just presented in terms of assessing risk to humpback whales under alternative management scenarios. It might also involve understanding the risk to the fishery from externalities separate from the entanglement threat, such as changes in market forces. And then what I'll spend much of my time on today is trying to figure out this last step in an IEA framework, which is what should we do? And I'll do that by evaluating alternative management scenarios that are hypothetical and using them to analyze the trade-offs in terms of benefits to whales and risks, cost to the fishery. So I'm going to start by building on what Karen presented with a retrospective analysis of risk to blue and humpback whales along the California coast over the last 10 Dungeness crab fishing seasons, alongside an interrogation of changes in revenue to the Dungeness crab fishery. I'm going to be focusing in on the regions you see here, Central California versus Northern California, as well as the entire state, in addition to thinking about the biologically important areas for humpback and blue whales outlined here in red and blue. And to do this, I'm really going to be standing on the shoulders of giants and all the talks that you've heard over the last couple of weeks. I'm going to be using predictions from the model that Brianna Abrams presented for blue whales, as well as the model that Karen Forney presented for humpback whales to describe the distribution of these whales in different Dungeness crab fishing seasons. And I'm also going to build on the fish ticket informed VMS data that Blake Feist and Owen Liu presented in an earlier module to look at the co-occurrence of whales and fishing activity over the last 10 years. And finally, because the vessel monitoring system data allow us to evaluate the amount of revenue that came from different locations in the ocean, I'm going to use those data to say, well, how valuable are those particular fishing grounds where risk is higher and lower? So we just dive right in here, as you could see from Karen's talk, for humpback whales here on the bottom row and blue whales in the top row. The risk to these whales increased markedly in between those vertical red lines. So that's from the 2014-15 Dungeness crab season through the 2017-18 Dungeness crab season, and they've since come down. And if you saw Jared Santora's talk earlier in this workshop, you'll know that one hypothesis that we think explains this pattern is that the cool, productive waters were compressed near shore into areas that have historically been the most fertile Dungeness crab fishing grounds. And if we try to look at that based on Brianna and Karen's blue and humpback whale models, what we can see is that there's been a real change in the expected abundance of blue whales on the left and humpback whales on the right from 2014 to 2018 relative to the 5 years previous. And that's what you're seeing light up in green and yellow on these maps. This all reflects an increased expected abundance of these whales. And this is limited to areas that have been Dungeness crab fishing grounds over this 10-year time period. So this is happening within fishing areas. If we look now on the right at what was happening with the Dungeness crab fishery in California, and specifically focusing on the vessels that have vessel monitoring systems on them, what we can see is that during this period from 2014 to 2018, when there was intense habitat compression for the whales, we saw a mixed performance of the fishery, with a couple of particularly poor years in 2014 through 2016, and then a couple of pretty good years from 2016 through 2018. And so with this backdrop in mind, I'm now going to launch into a bit of a thought experiment, or if you're my kids and prefer Bear Grylls, you can think of this more as a choose your own adventure of trying to rewind the clock and ask, well, what would have happened if we would have taken management action back in 2014 and 2015, or in the 2009-2010 crab season? How would that have influenced risk to the whales, and what would have been the cost to the Dungeness crab fishery? And in particular, I'm going to focus on 4 types of management actions. These are all hypothetical. These include delayed openings, where the crab fishing season would not have opened until December 15th, early closures beginning April 1st, gear reductions to 50% of what actually occurred from April 1st to the end of the season, and depth restrictions, meaning no Dungeness crab fishing seaward of 30 fathoms beginning April 1st. I'm going to consider these individually as well as combinations of them, implemented at the scale of the full state of California, just in Central California alone, as well as in the biologically important areas for humpback and blue whales. Now, to understand how these scenarios influence outcomes, I'm going to focus on the expected risk reduction to whales shown here on the y-axis. So the greater the risk reduction, the better for meeting our goals. And the expected changes in fishery revenue. So the closer we are out here on the right-hand side of the x-axis, the closer we are to the 100% of the revenue that actually accrued during a fishing season. And what I want to point out in this framework of a trade-off analysis, this red line represents an efficiency frontier, or the optimal outcomes for maintaining a given level of crab fishing revenue for a specified amount of whale risk reduction. So you don't want to be in here where whale risk goes down, but that's come at a great cost to the crab fishery. If you're going to try to reduce whale risk this much, you want to be all the way out here and use a management strategy that'll get you there. So let's dive in and look at some of the results. On the left, we're going to have blue whales, and on the right, we're going to have humpback whales for the next 3 slides. I'm going to try to make 3 points. The first is that in the 2014-18 time period for both blue whales and humpback whales, the expected reduction in risk to the whales was greater than in the previous 5-year time period. And that's whether we're looking at delayed openings, early closures, or depth and gear restrictions. So that's the first point, is that risk reductions were greater during that 2014-18 time period, although a bit more variable. The second point, as you can see in these blinking dashed circles here, is that depth and gear restriction type management actions were expected to reduce risk substantially. And that's compared to, say, something like a delayed opening, where because this is a derby fishery, a lot of the effort from a delayed opening just gets pushed forward into the year. The third point I'd like to make from this slide now compares these management actions implemented at the scale of Central California on the left during each time period, or statewide in both Central and Northern California. And what you can see is that all of these lines move up and to the right. This implies that the expected reduction in risk to both blue whales and humpback whales is greater if the management actions occur statewide. And that makes sense. If a bigger region has fishing restrictions, there are fewer lines in the water, we would expect there to be lower risk to whales. Now, I promised you that this wasn't just going to be a talk about risk to whales, but also about cost to the fishery. And so if we now look at the expected cost of the fishery under these different management scenarios, I can make 3 points here as well. First, the costs were greatest and most variable in 2014 to 2018 here on the right. Second, the gear and depth restrictions, as you can see in the dashed circles, were less costly than, say, something like an early closure. Those are the triangles. And finally, statewide management actions, while we saw on the last slide, reduce risk to whales the most, they also cost the fishery the most. Now, you might be wondering, and I've heard a lot about the heterogeneity within the Dungeness crab fishery. And so I'll just briefly say that we've looked at this a little bit just in terms of the impacts of these management actions on small vessels. And what you can see here is that these lines all kind of go straight across. And that implies that the expected change in revenue to the small vessels are roughly similar under all of these management scenarios as they are for the fleet as a whole. Finally, I promised to talk about this in terms of trade-offs, and so I want to orient you to this figure. In the first 5-year time period, we're looking at the top row, the 2014 to 18 time period, we're in the bottom row. We're looking at blue whales on the left and humpback whales on the right. And again, this is thinking back to those efficiency frontiers. You want to be out here. And what we can see is that the trade-offs have become more stark. So whereas in the earlier time period, the expected cost of the fishery were on the order of 5 to 15%, they've up to tripled in the later time period, with only an expected benefit to whales of a 20% increased reduction in risk. So these trade-offs are more intense. So just to wrap up, I'd like to close with a couple of take-homes. Management strategies have really different benefits to whales and cost of the fishery in different years, and presumably under alternative ocean conditions. And that means that the trade-offs that accrue to the fishery and to the whales are different in each year. And by using this efficiency frontier framework, we can identify those that are optimal given a fixed amount of risk reduction to the whales. Second, the depth and gear restrictions in spring alone seem to provide substantial risk reduction at lower cost of the fishery and may be simpler to implement and more easy to communicate. Finally, this is all rewinding the clock and looking backwards in time. Of course, the challenge is knowing where we are now and looking forward. And so that really points to the need for development of forecasting tools and determining the performance of these types of management actions moving forward. My colleague Chris Free, who's talking next, will get into a more forward-looking analysis of management strategies that also builds in some additional complexities like consideration of domoic acid concentrations and reactive measures from the management community in terms of changing ocean conditions and whale abundance. Thanks very much for your attention.
Thanks very much, Jamil. That was great. And I think we'll need to move on, but I did want to pause for one clarifying question, and this maybe for Jamil or Karen. I'm curious, as you looked at risk, how much did you see the variable whale dynamics affecting risk versus variable fishery dynamics? Is there anything to kind of draw conclusion-wise there from what might have a greater impact on risk year by year?
I can take that briefly.
Yeah, go ahead, Jamil.
The answer is it depends on which year we're talking about. In 2015-16 in California, with the long delay in the Dungeness crab fishing season opening, was certainly a combination of anomalous whale distributions in combination with spring fishing season that is not normally as intense. However, in other years, it does seem that the Dungeness crab fishing areas were similar to where they've been historically, and it was the elevated whale abundances that were likely a strong contributor to the entanglements that we saw.
Great. Thanks, Jamil. All right. Well, we will continue on with questions as time allows when we wrap up. But for now, I'd like to pass it over to Chris Free to take it away and continue on.
All right, can you see my screen? Okay, I'm gonna assume so.
Yes.
Great. So I just want to start out by thanking the organizers for putting together such a great entanglement science workshop, and for all the participants for your engagement throughout the workshop. The discussions have been really illuminating, and I'm looking forward to the discussion following this. So I'm presenting this work on behalf of a large project team that spans co-authors from UC Santa Barbara, from the Nature Conservancy, and NOAA, and UC San Diego at the Sencus. And what we've really tried to do here is put together a management strategy evaluation model that we can use to test and compare different strategies for reducing whale entanglement risk in the California Dungeness crab fishery, and really measure trade-offs between those strategies, much in the lines of the way that Jamil just really well introduced. So our goal here is to put together a simulation framework that we can layer different management strategies on top of, and measure their trade-offs, and try to really find strategies that are successful at resulting in low numbers of whale entanglements, but also maximizing fishing opportunities. And in testing and comparing these different management strategies, we don't want to just find strategies that perform well in one year. We want to find strategies that perform well across years under different types of uncertainty. So strategies that perform well in years that have early season closure or season delays due to domoic acid or meat quality, and also perform well in years that have particularly high whale density or anomalous whale dynamics. I just wanted to sort of introduce what the results of our simulation sort of can and cannot say. So it cannot perfectly quantify exactly how many whale entanglements would result from a particular strategy, or how much lost catch would result from a different strategy. But it does become a platform for comparing the relative performance of different strategies. So we can say this strategy is likely to result in fewer whale entanglements than an alternative strategy, or more lost catch relative to an alternative strategy. And we're going to be searching for those strategies that seem to produce the fewest whale entanglements with the least impact on the fishery. So to do this, we built a simulation model that simulates all the components of the system, so that we can layer on different management strategies and see how well they perform. So we have 4 different modules. We have a module that is simulating the crab population dynamics off the coast of California, simulating the dynamics of the fleet that is going out and targeting that resource, and then simulating the density and abundance of whales, and their sort of co-occurrence that we've heard about with fishing dynamics. And finally, we want to make sure that we test the robustness of the strategy to closures resulting from domoic acid or meat quality. So I'm going to briefly introduce each one of these components and sort of give you some intuition about how the simulation works, and then we'll dive into some preliminary results. So the very first step is we need some way of simulating the crab population dynamics. And so we simulate every single season. Sorry, I should have said earlier, but we're simulating on weekly time steps across the past 5 seasons, and we're simulating the abundance of legal-sized male crabs. And every season starts with preseason legal-sized male crab abundance as estimated by Richardson et al. 2020. And we distribute that abundance of crabs into California commercial fishing blocks based on the fish ticket data collected by CDFW that has block level catch. So every season's abundance begins with this. Every season begins with this abundance, and that abundance gets distributed in proportion to where catch came from that season. Then we need a way of simulating the fleet that is targeting that resource. So we reconstructed historical fishing effort based on that fish ticket data, where we make the assumption that every vessel is deploying all of its traps every week that it is going out and fishing. And you see that sort of reconstructed fishing effort for the past 6 seasons plotted here. And from those reconstructions, we can learn a little bit about how to simulate the fisheries. So we've tuned a fishing dynamics model that reduces effort in response to declining abundance as fishing is removing crabs. And so just sort of briefly, the model works where the season opens with 130,000 traps. And that weekly effort declines as abundance of the crabs decline. We simulate the distribution and density of whales using Karen's humpback whale species distribution model, which we heard about in detail in Module 1 and were reminded of in the last 2 great presentations. And so this model sort of allows us to represent the weekly number of whales in every single one of these California commercial fishing blocks, and it's capturing that seasonal migration and capturing variability in between years, so that we can test strategies over years with different whale dynamics. And then from this, we need some way of being able to calculate the sort of, as we've been talking about, the co-occurrence of the fishing fleet with the whales. And we do this in a slightly different way from the other presentations so far, where we actually estimate the likelihood that a trap will encounter a whale. And we define an encounter as a whale passing within 1 body length of a trap. And so we're actually borrowing a really simple equation from ideal gas theory that suggests that if you know how many whales are in a block, and you know sort of about how fast they swim and how big they are, you know how sort of efficiently they're searching for a trap, and you know something about the likelihood that a trap will encounter a whale, again, a whale passing within one body's length. And then we're able to use that we're able to reconstruct the sort of number of historical encounters that have occurred over the last 5 years, and compare that to the number of confirmed entanglements, and calculate a probability that an encounter leads to a confirmed entanglement. And this becomes a way in our model of not only measuring the number of encounters, but measuring the number of potential entanglements as well. And I just want to remind everyone, this number isn't 100% correct, but we're really interested in the relative performance between measures. So it can't say with exact precision the number of entanglements that will result from a management strategy. And the part we're still working on right now is to test the robustness of different strategies to historical closures resulting from domoic acid contamination, and meat quality, and also simulated closures resulting from those 2 processes. So Now that we have this like framework for simulating the entire system, we need to layer in the different types of management strategies that you would use to reduce whale risk. And we've designed the tool to be very flexible, and we have a bunch of different management dials. We can look at entanglement triggered sort of closures or gear reductions. We can look at closures or gear reductions that get triggered by the density of whales in a zone. And we could add in flexibility about how long one of those management actions, how long it lasts. And I just wanted to say we haven't tested the ramp procedure specifically because they're sort of a moving target and are a little bit vague about the marine life concentration triggers, but we've borrowed a lot of those management instruments from those procedures. And then to measure and compare the performance of different strategies, we are using 4 different performance metrics where we measure the amount of total catch, and we measure the amount of time on the water as a sort of measure of fishing opportunities, and are currently working to translate that total catch into revenues. And then on the whale side, we are quantifying the number of trap whale encounters and also the number of trap whale entanglements. And we look at both of those metrics because the trap whale encounters is something we know for sure in the model. And the entanglements part has this random probability. It might be high in bad years or low in really sort of lucky years. So in this presentation, I've sort of selected a couple of different management scenarios for us to look at. The very first is the closure of a zone based on a survey in the fall or spring that determines that the density of whales throughout that zone is above a specified threshold. So we're going to look at 3 different sort of thresholds for triggering those zonal closures. And another type of closure, which is a statewide early closure, which Jamil talked about in the last presentation. And we're also going to look at 3 levels of gear reduction that happen at the beginning of the season: 10% reduction in gear, 20% reduction in gear, or a 30% reduction in gear. And we can each one of these dials can be sort of adjusted to evaluate different levels of these parameters. So I just wanted to go into some of our preliminary results and see how these different management strategies perform across our 4 different performance metrics of fishing weeks lost, catch lost, number of whales, number of trap whale encounters, and then the number of entanglements. So in this first performance metric, in terms of fishing weeks lost, we see that the early closure would result in the greatest loss in the number of fishing weeks available, and the gear reduction scenarios result in no lost fishing weeks because there were no closures, and intermediate numbers from the MLC triggered closures. Then we can look at terms of the proportion of lost catch. So even though the statewide early closure results in the greatest loss of fishing weeks, it results in the least amount of lost catch because it's a derby fishery, and so little effort is happening at that time of the year. And then you see that sort of other patterns in the amount of lost catch across the marine life concentration triggered closures and the season reductions. Then we can look at how much these management strategies will reduce the number of encounters relative to a sort of business as usual no whale risk management scenario, which is represented by this dotted line at the top. And here we see that the statewide early closure and the gear reduction scenarios might perform best in terms of reducing the number of encounters, and that gets reflected as well in terms of the number of entanglements. Just to conclude, we have developed a really sort of flexible tool for measuring trade-offs between alternative management strategies. And in using this tool, we found that whales are present throughout the fishing season coastwide, and that the extent of zonal closures will be really sensitive to the density trigger that triggers a closure, and also the layout of the zones and the survey design that judges that threshold density. We found that zonal closures may not reduce entanglements as much as expected because effort gets displaced and concentrated elsewhere. So effort might end up in places of sort of medium-high whale density. In sort of simulations I haven't shown here, we found that mid-season gear reductions aren't as likely to significantly reduce the number of trap whale encounters because effort has already declined so quickly. And finally, early season gear reductions seem to maintain high catch while also reducing the number of entanglements sort of comparable to those levels achieved by zonal closures. So thanks for your attention.
Awesome. Thanks so much, Chris. I think to make sure we get through everything, I'm going to hand it straight over to Burton for now, but we'll circle back with some clarifying questions as we have time before the discussion. So Burton, welcome.
I'm here.
Hi, Burton.
All right. All right. So thanks much for inviting me to join in and talk on this. I was sort of asked to provide a perspective of sort of a similar issue that we're dealing with on the East Coast. And in many ways, it's remarkably comparable to issues that people are facing there on the West Coast. In our case, it's North Atlantic right whales and the lobster fishery. And some work that we've been doing on sort of comparable models for dealing with this. Putting together these models requires a huge amount of data and contributions from a large number of people. So Protected Species Branch and Ecosystem Dynamics Assessment Branch from the NAFSC, Protected Resources Division from the Regional Fisheries Office, Industrial Economics, which is a consultant working with us, Duke University Spatial Ecology Lab, which is where most of our whale models are coming from, some data shared from Maine Department of Marine Resources, New England Aquarium, and then the North Atlantic Large Whale Take Reduction Team, which was the group who got to first test the system out as we were developing it. So sort of the background for this is that prior to 2010, our serious incident and mortality rates for entanglements in the lobster fishery were above PBR, but the population was still declining. Was still increasing. In 2010, we saw this regime shift happen in the Gulf of Maine, and of course, you saw something similar on the West Coast that you've been dealing with the heat wave and the blob. But with this regime shift in the Gulf of Maine, the productivity of the seasonal feeding grounds declined. We saw a sudden shift in the distribution of whales, including a lot of them moving to Canada, where they normally were. Female calving rates have decreased. And as a result, the population has been dropping precipitously over the last few years, both because they're reproducing less and we're seeing more entanglements, particularly in areas that they haven't been in the past. And therefore, people really weren't prepared for them to show up. And so we suddenly found ourselves needing to decrease our entanglement rate, and along with that, a parallel need for a tool for assessing if a model was actually going to accomplish what we needed. So we ended up constructing what we call the Right Whale Decision Support Tool. This was built to assist managers, decision makers, and stakeholders by visualizing and understanding the spatiotemporal overlap between the lobster fishery and the North Atlantic right whale, and modeling how risk of entanglement may change as a result of management action. Within the model, we're dealing with primarily, one, the density of vertical lines, and what we added into this was the threat posed by different vertical lines given different configurations in lobster gear. And then the third term in this product is the densities of right whales. So 1 and 3 together are basically a co-occurrence model. But we felt a real need to sort of include this threat because there's so much heterogeneity in the gear configuration for the lobster fishery. We have people fishing relatively light gear inshore, fishing singles, doubles, and triples. We have people offshore in deep water with much heavier gear fishing 35 to 50 pot trawls. And we needed to recognize that those two different gear types probably pose different threats to whales and needed to capture that. It doesn't deal with a lot of the complexity that we wish it could, and these are sort of a checklist for the future. We don't have whale behavior, we don't have information, or we don't include information on adjacent gear density because you may get entangled and then drag that gear into adjacent gear, which then complicates the entanglement. Spatial temporal variations, environmental conditions, which is where you have slack lines versus lines under tension. And we're not addressing ground line between the traps and the lobster traps that's associated with threat to the whales. So this is just the vertical lines in the water that we're looking at with this. The domain for this model includes coastal Maine down through New Hampshire, Massachusetts, and coastal Rhode Island, out to the international boundary, and then much of the continental shelf. This is the vast majority of the lobster fishery, and there wasn't enough data to sort of parameterize the model down below this. This model is set up to run at a resolution of 1 nautical mile. But not all, and in fact, not most of our data is available on this resolution. So there's some downscaling to sort of reach that resolution, but allowed data sets of different resolutions to sort of be mapped over top of each other. For setting up a model for a run, you can specify fishery constraints. So you can pick a fleet that you want to do the model run for, spatially constrain it to a geographic area. You pick your whale distribution model, you pick your gear threat model, and there's a number of other switches that you get to throw at the time that you set this up. And then you pick your management options that you want to put into place, and these are implemented in space and time. So we do trap reductions, trap caps, spatial closures, which can be seasonal or year-round, changing trawl measures, which is the number of traps that end up in a trawl, end line measures, which is whether you have 1 or 2 lines on the traps, whether you have some portion of the fishery fishing ropeless gear, and then rope strength measures. So the potential for switching to lighter rope, putting weak insertions in your lines, those sorts of management options. The information flow through this, this looks fairly messy, but really it's a fairly straightforward numerical model. You basically start off with a map of where there are traps, and then you have submodels that tell you how to translate traps into trawls, how to translate trawls into end lines. And once you have the trawl length, then you can get the rope strength associated with the trawl of that length. And then the density of end lines and your rope strength together give you the threat associated with that gear. And when you combine that with your whale density model, you get sort of a risk value for that location and in that time. There's a series of submodels that basically clarify how to translate from one gear type to the next as you move down through this. And then you have the user inputs acting on these and changing them. So once you run the model once, you get a default run, which is basically the results of the model with no management action, and then a scenario run that implements whatever user inputs you wanted to change things. And then the outputs give you comparisons between the 2 risk models that come back from that. So as examples, this is, I think, vertical line densities. This is by month and across the domain of the model. In some of these areas, you can see sort of homogeneous regions, and this is really just the resolution of our data. We don't have VMS on these boats. We don't have spatial reporting for most of these boats. So all we can say is that gear is homogeneously distributed inside whatever polygon they're reporting fishing in. So it's a real constraint of spatially how well we can tune these. And then the example of a whale model. So this is from Duke's Spatial Ecology Lab and Jason Roberts' work. And we get a monthly estimate of where and when the whales are at. And you combine those in with that threat model, and we get a final risk map back from this. And one of the keys that's interesting is this, is that the final risk map doesn't really look like either the whale or the gear model inputs. It's really where they're sort of overlapping at moderate densities that you tend to have some of the highest risk levels. The gear threat modeling itself has turned out to be one of the biggest challenges for this, partially because other data sets are broadly recorded and readily available. But how to understand how different gear configurations have different threats to whales is challenging, because you're necessarily attempting to distill factors that contribute to complex outcomes for events that are generally rare and not directly observed. Most data for whale entanglements come from mortality or disentanglement events, both of which take place a considerable amount of time after the entanglement took place. So you're not witnessing the entanglement. You usually can't trace it back to where it originally occurred or what the original gear configuration was. And generally, they're not carrying a complete set of gear, so you don't know what they originally encountered. And if a lot of this data that we have is coming from disentanglement, and they don't disentangle minor entanglements. So you only get data on what major entanglements are. You don't get a sense of what less dangerous gear looks like. In a beautiful day, we would have data sets that would allow us to look at this as a series of processes. You have a whale encounter and the factors that lead to that, what leads to entanglement, whether the gear anchors on the bottom or not, and what happens as a result of that. And you end up with a series of outcomes, and then you would then be able to score each of those outcomes. This is what I call my naive attempt at process-based modeling for this, because I'm not a whale biologist. And when I presented this idea, everybody said, we don't have any of that data. So we scratched their heads and went through a whole series of increasingly simpler models. And we're simply data limited on being able to fill this in. The one process we were able to see largely comes from a paper from Knowlton in 2016, which is just the observation that larger whales often are carrying heavier gear than smaller whales. So by species, heavier braking strength ropes are associated with larger whales. Within species, within species, you see variations by age and by size. So we thought, okay, maybe the one thing we can kind of get out of this is rope strength. So we're trying to quantify this threat now, a very simple model based on rope strengths associated with different gear configurations. And the question is really whether we could detect if different rope strengths were either over or underrepresented in whale entanglements. So we had some rope strength data that came from this Knowlton 2016 paper. And then we basically did a co-occurrence model to understand what weights of ropes whales were encountering. And what we get back is distributions of rope strengths for right whales and humpbacks in this domain. And we see that we think the right whales are encountering some marginally stronger rope than humpbacks are, because they perhaps tend to be a little further offshore. And so then we can look at this expected encounter rate, which is the black line, to the blue observed encounter rate, which is our actual data, which again is a pretty sparse data set. But the expectation is that the heavier lines should be overrepresented, so above the black line, and the lighter lines should be underrepresented. And at that point, we can look at ratios of the observed to expected. We get different models for humpbacks and right whales. And that turns into threat models by the two species. Because we were concerned about some being able to portray uncertainty in this, we use this bootstrapping then to give us basically upper and lower 95th percentiles on this threat model. And then that's included in the output for these models. And I think that my time is up, so I'll stop there.
Thanks so much, Burton. That's very